Welcome to the first of our biological anthropology seminars this year. Kate has introduced the seminar series itself. I'm just going to introduce Oskar Burger. I haven't really thought about this because I know Oskar. We worked for a year together at the Max Planck Institute. So what can I say about you? Oskar is a very nice guy. Started his career in New Mexico with those big guys like Charnow and life history theory and so on, coming from archaeology. Then he was a postdoc, affiliated with the University of Stanford. Then went to the Max Planck. Now he's in Kent. Yes, he's in Kent. Yes. Anyway, I wasn't sure about the precise topic of the seminar. I can say Oskar has done very interesting work recently. He has published a very interesting article on the evolution of post-reproductive lifespan in humans, and readdressed the issue of the evolution of menopause and so on. He's also published a very interesting paper in PNAS on changes in patterns of aging in humans, comparing aging in hunter-gatherers and historical societies. So Oskar's approach is demographic. He looks at demographic data to analyze changes in human life history. Today he's gonna
we'll just see.
more or less the same, and discuss variation in the rate of aging, focusing on how to interpret the process of aging from a demographic perspective, right?
Yeah.
I think that's enough. Okay, well, thank you.
Perfect. Thank you, Lucio. Appreciate it. And that was a really good introduction. It set it up perfectly. So I had these two papers that were about aging-related things, one of them being post-reproductive lifespan and one of them being just a very big picture comparative thing about mortality improvement during the last couple of centuries. And both of those things led me to get more and more involved in the biological study of aging and kind of what's under the hood in terms of what we see when we study demographic aging rates. And that's what you're going to see today. So when we study aging, yeah, okay, there we go. There's some really exciting, universally interesting stuff about aging, right? Like, we're all kind of wondering about when we'll die and why, and there's all this popular culture research going on that's in the news all the time. So this is just from a pop culture website yesterday, and it was all about this new research looking at healthy lifespan versus improvements in longevity. And there's all kinds of stuff about creams and all this stuff making the news all the time. And there's also things like the grandmother hypothesis and why we have a post-reproductive lifespan that, from an evolutionary anthropology view, is like really pretty sexy and pretty interesting. Here we have another pop culture thing showing that, in fact, as our life expectancy improves, that the fraction of it that we spend relatively healthy is also increasing, counter to relatively popular belief. And this stuff is making the news all the time. So there's this kind of inherent interest that we have to it. But then in terms of why we care about aging, that's supposed to say, yeah, that's fine. Exiting, it's supposed to say exciting, actually. So there's a very much less intrinsically interesting aspect of aging research, which has to do with how we measure it accurately and how we predict what should happen as a function of various ecological changes. And unfortunately, a lot of it looks like this, and this is why we tend to ignore it, right? It's pretty intimidating. This is from a paper that my co-author did, so he's one of those guys. And so unfortunately for you, I'm really not talking about this much at all, and the reason is that I've fallen into a trap that a lot of us fall into, where I take received wisdom about the theory of aging as for granted because it sounds so nice and everybody else is using it, and I've ignored a lot of the progress that's gone on the theory of aging, and also a lot of areas where there's tension between theory and data, and we tend to still use the theory and ignore the exceptions, of which there are more and more all the time. So from that perspective, I think that there's been a real stagnation in progress, because we're stuck with the old kind of theory, and we don't really tend to include it when we evaluate mortality and aging research. And I'm talking about this in part when I was emailing with Kit. He mentioned that this was some kind of there would be a bunch of new master's students here, right? Is that you guys? So you're just out of uni last year, more or less, on average, and you're trying to think about what kind of research you want to do in evolutionary anthropology, right? So that's my working assumption. And I was like, well, how can I make it so that when you get into the literature on biology of aging, that some of the stuff that sounds really technical and boring is at least you understand why people talk about it. And I'm not sure that I'll pull that off, but that's kind of the goal for getting into some of these things about the Gompertz equation and how it works. So we'll see how that goes. So there's a lot of things, like a very textbook aging prediction is what we call Williams' hypothesis. It states that if mortality drops, that the rate of aging should drop as well. And this prediction was never actually true. And yet you see papers every year that state it, and they make a big deal out of testing it because it's so easy. And that's the kind of thing that I want us to get away from. So an outline, because of this stuff of trying to do some background catch-up demography 101, I've got a thread that actually is just a straight-up hypothesis test kind of study, and then I've got this thread where I jump off of that now and then, and I try to do some background. That might lead to total chaos, and if so, just throw things or ask questions or whatever, but hopefully it kind of works out in the end. So we're going to talk about the Gompertz equation and why we use it to measure aging. There's a feature of the Gompertz equation called the Strehler-Milban correlation. At the very least, you'll now know what that is. If you don't already, I would expect that you don't. And then there's an anthropological application where somebody has tried to make an evolutionary argument about the difference between both fertility and mortality in chimps and humans, that's evolutionary in nature, that is based on an interpretation of this correlation. So that's where at least there'll be something hopefully quasi-interesting. But in order to understand why this matters, we have to go under the hood a little bit and look at the theory. So we're going to evaluate this hypothesis with some explicit tests, and this is where the boring and the exciting come together. Wow, I've got this exiting thing again. Huh, it's interesting. And if time, we'll talk about Hamilton's indicators and a critique of this classic prediction. We'll see how that goes. So one of the things that I've been interested in from an evolutionary anthropology perspective is maybe how phenotypic traits have changed over the last few hundred years, especially at the population level. So we know that there's been a lot of change in lifestyle and diet and group size and mortality rates and access to energy and all this stuff, family size, fertility intentions that have occurred very recently. And it's not very clear what those things should do to our life history. How should our life history adjust in the face of all this change? And that's something I've gotten very interested in. And of course, aging and having an increasingly elderly population is a big part of this switch. Have you guys seen this before? Is this a plot that everybody's familiar with? It's great if you could say no. Please say no. No? No's? Okay. So this is something when you're at the Max Planck Institute, you see this almost every day until you kind of want to puke now when you see it. But it's published in 2002 by two of the main demographers in the building. It shows that the best life expectancy at birth has been increasing linearly as a function of time since 1840. So every one of these data points is for the country that in that year had the best life expectancy at birth. And it seems like kind of a trivial thing, but when you think about life expectancy at birth, it's a complicated life history characteristic that results from all kinds of interactions among people and with their environment. And anytime you get a straight line fit with an R squared of 0.98 across something that's so inherently complicated, you really have to sit back and go, huh. Right? Like if we were Drosophila biologists and we introduced a treatment and we got this result from our cohorts of Drosophila, we would be like doing cartwheels in the street, right? This would be an amazing finding. And we don't really know why this happened. We know that hunter-gatherer lifespans can get up into this range, and we know it was very, very recently that our life history went into a different area. Something else that's going on in this plot is that every one of these lines, it was a published forecast of what the upper limit of human longevity could be. And so a lot of them were broken already when the paper was published. And we've repeatedly failed to forecast what the upper limit of longevity is. And it's interesting that we're so bad at that, given how much interest there is in understanding human life history from both a health perspective and a life history perspective, right? But you can, in terms of highly quotable, gee, Mom, guess what I learned in school today kinds of stuff, this one's pretty good. You can say your life expectancy goes up 3 months a year every year, a few hours a day. Just by sitting here, you're living longer. What are you going to do with all that extra time? It's kind of good news. And so just to put that in another perspective, here's every country in the world for which we have data, life expectancy at birth. The blue bars are 1800, and the red bars are 2000. So there's almost no overlap. We have the very sad case of Sierra Leone here is the only country that's still within the 1800 range. And the fact that in 200 years, the worst countries in the world are now doing better than the best countries in the world 200 years ago is amazing, right? I'm just trying to put this big improvement in context. And if we were paleoanthropologists and we had this kind of distribution for any phenotype, we would say, oh, this is speciation. But this clearly cannot be that, right? So it's a pretty amazing bit of improvement. Going to there's a lot of stuff that is received demographic wisdom that you hear in popular culture and when you talk to the news, media, and all that kind of stuff. And so anytime you talk about how much life expectancy at birth has improved, you always hear, oh yeah, that's just infant mortality. That's all that is. And as soon as infant mortality improves, the idea is that life expectancy will quit improving because everybody lives to be 15 or 20, and then after that it was always the same. But what this graph shows you is that's very definitely not true. This is the odds of living to age 15, and when those odds are well above 0.8, we're actually above this line. So life expectancy is increasing faster when the odds of living to age 15 are already really, really high. This is actually not directly relevant to the talk. I'm just throwing it in as a demographic tidbit for those of you who don't have background. And you do hear this in the news all the time, that all the stuff is infant mortality. That's where all the progress is made. And it's actually, maybe that was true before 1950, but it has been true in the last 60 years or so. So questions that we might want to ask, given how much progress we've made, how is this diversity and mortality pattern studied? We often use this thing that's called the Gompertz, and we'll talk about that in a minute. And what should all this reduction in mortality do to the human rate of aging? If our received wisdom is correct, it's supposed to be that when mortality goes down, that the rate of aging goes down. But then you have to ask yourself, is slow rate of aging what we want? Do you want to age slowly, or do you want to postpone the onset of aging and then age quick? These are some things that aren't really very well addressed by our classic theory. And so then it's just, what's going on with our human life history change and with all of this rapid major developments. So aging and senescence, there's two technical definitions of it. If you put in, I wanted to do a whole bunch of fun photos here, so if you put in something like celebrity and aging, you do get quite a few hilarious photos. Some of them weren't appropriate for a general audience, but there was a lot of humor to be found there. So we know that aging is something that we generally don't like. It comes with a decline in function and often a fairly radical change in appearance. And then so this is the kind of pop side of it, and this is from a detailed physiological study where we've got people who are under 30 normalized to 0 for VO2 max efficiency, which I honestly don't remember how they measured it, and peak sprint power. And with each increasing age group, there's reductions in all of those things. And lots of studies have shown that. So this is just one way that we think about aging. It's just this age-related decline. This is a very human-centric definition. As not all organisms do this, but most of them that we would study, birds and mammals, do. And then there's the boring kind, actuarial senescence. So this is when we're just taking population and we're looking at the mortality as a function of age, and we know that it tends to rise with age. And we want to study what causes variation in the rate of this increase, or the shape of the curves that we fit to the risk of death with age and things like that. And so when we talk about an actuarial definition, we mean this, this comes from actuaries or insurance people, right? They want to know what the odds are of certain types of people dying, so they know what to charge them for life insurance and things like that. And this is also, anytime we're just studying population level trends like this, that's what we mean. So what Jim Vopel would say is that the odds of living through the year is the best measure of health you could ever come up with. And in one sense, I think he's right, although there's other aspects of health that are of concern. And the assumption underneath this is that the population level summarizes the average physiological state of individuals. And that's an important point for later, so save that in the memory bank. Oh, and I'm talking about this as if mortality were the only thing that we mean when we talk about aging and senescence, but of course we can talk about senescence and reproduction or other traits. Some people would measure senescence solely as a function of fitness. You could take a combined measure of fertility and mortality and put them together. One of the things that's important for humans is that our reproductive system and our somatic system tends to senesce at different rates, but that's for another talk. So this is where we're just doing a very quick crash course in demography, and we're talking about how we actually study this stuff. So this is what's known as, well, dx. This is the density of deaths as a function of age. So what this means is that when this curve is higher, there's more deaths at that age, and when it's lower, there's fewer deaths at that age, right? So that's pretty straightforward. And when we're studying populations in nature or in demography, how we really, the basis, the underlying thing is always this. So if we were studying rabbits in a field and doing an ecological study, or if we were studying humans, we would want to go out, find people that were born about the same time, and we would want to go back at regular intervals and just figure out how many had died each time, right? And from that, we would know, as a function of age, what the frequencies of deaths were. And once we have that, then we can do a bunch of other calculations that put survival in the kind of maybe more typical kinds of plots that you're used to, right? So this is proportional live. Has everybody seen one of these? This is just a standard survival curve, right? So for the populations that we have here, you'll notice this is Germany in 2010. Basically, any country in the West would look just like this: England, UK, whatever, Sweden. And what you see is that there's almost no infant mortality, and all of the deaths are now amassing at very late ages, 85 in this case. And what you see here is that France in 1816, and this is an aggregate of several different hunter-gatherer populations. It's also highly smoothed. And you'll notice that even in 1816, a fairly wealthy country like France was probably not out of the range of variation for the hunter-gatherer survival experience. It's hard to put error bars around this, right? Like if we could go back through the last 100,000 years and sample thousands of populations, you can imagine that the error bars on this would be really, really huge. And it would most certainly encompass what the West in Europe and all of what we would have experienced until at least 1900 or later. You'll see more of that in a minute. So this is our typical measure. I would assume that people are familiar with that. And these are the exact same data sets, but I would guess that maybe people are less accustomed to seeing data like this. But this is, in fact, the kind of raw data, what they really look like. Even more common is to look at things like the probability of death. I like this one because it's easy to interpret. You can say if the probability of death is 0.1 here, then 1 out of 10 people will die, 10 out of 100, that kind of thing. So it makes it quite easy to interpret. And then I'm just going to do the log of this one. Everybody knows how to use a log transform, but it's one of those things that often the change in the nature of the curves is bigger than you expect if it's not something you're used to doing. So those are the exact same curves. And log transforms, of course, tend to increase differences at low values and decrease them at larger values, because now down here the difference is absolute or additive, and over here it's multiplicative. So we're talking about how many times lower the mortality risk is. And again, we see that our hunter-gatherers and our Frenchies are really, really close together, and we have this huge reduction just in the last 100 years. There are several measures that are similar to Q of X. Like when we talk about a mortality hazard, it's a slightly different calculation, but it looks just like this. So this is the kind of thing that we fit data to, right? Fit curves to. So again, this is our underlying data set, this really exciting death distribution. What I've done here is put dotted lines for where the life expectancy at birth is. And so when people talk about life expectancy at birth being a biased measure, I think they're wrong to call it biased per se, but the thing is that when people have in their mind life expectancy at birth, they want something that gives them the age where people they actually the mean age at death for people who are old, right? And so you see here that for hunter-gatherers, you do have a bump out here at 65, and yet life expectancy at birth is way down here at 30. So a whole lot of people live more than twice the life expectancy. But in countries like the UK today and Germany, life expectancy at birth is almost to the modal age of death. That's just for background as you go forward in your demographic lives. So now we're going to talk about the Gompertz mortality curve as the main tool for documenting mortality change and aging. So this comes from Benjamin Gompertz, who published this a very long time ago, 1825 I think was the paper. And it's just this quite simple equation. This is just the hazard of death, or you can think of it as the risk of death in the year. It just has two parameters, A and B, that if you log transform, right? So if we move from this to this, now we're just talking about a straight line, and it becomes quite easy to interpret. So when we log this, we have an intercept, a slope and an intercept. And the way that people interpret these is that this is the initial mortality, this is the mortality rate when aging starts, and this is the rate of mortality. This is how quickly it increases as a function of age. So it's just like an equation for a straight line, and it gets used a lot. And we don't have like a real theoretical basis for it. Well, that's arguable, you could say. I'll come back to that. But he just realized that the susceptibility to death should increase with age, and he selected an equation that would capture that, and lo and behold, it fits data on mortality extremely well in all kinds of populations for all kinds of species. And so this is what it looks like when you have them plotted out. So this is our unlogged form, and so the idea is the red curve has higher mortality when aging starts. The blue curve has lowest, and you can see that they're rising at different rates. Over here, it's harder to see which one has the steepest line, right? It's because that we have to try to interpret this as exponential, but when we log them, it's clear that these two have pretty much the same rate of aging, and this one has a faster one, right? So lower mortality early, but maybe you would say it has a faster rate of aging just because it's steeper. And that's how you interpret this stuff. It's just that simple. How are we so far? Okay? Sure? Moya? I know you tell me. All right. So why do we use the Gompertz at all for aging research? I mean, it fits very well. We have an issue that it's not always clear which range of ages to fit it to. It's usually 30 to 80, but there's really is no way to say for sure what is the ideal. It comes from a set of distributions that are designed to model extreme values, and I think I get that in the next slide. And it's derived, when we talk about extreme value analysis, there's a distribution that does that called the Gumbel. I'm going to bore you with this. This is the worst, so just brace yourself for like 2 slides, and then it's back to normal land again, okay? But this is really pretty important, because a lot of people say that the Gompertz has they basically call it an atheoretical model. And that's because we don't have like a Charnov-style derivation of, if species that are similar in this parameter also do this, then aging should go this way. We don't really have any kind of a priori life history understanding of it. But it turns out that if deaths are distributed like this, remember that we tend to think of things as a straight line in the hazard space, but the actual data are like this. It's a distribution of deaths. And the way that we get that is we have this Gumbel distribution, which is designed to, both of these distributions are designed to capture what is called extreme values. So these are maxima and minima, and if you want to think of death as minimum time to a failure. So you have something in your body that keeps you alive, and death is the minimum failure time to when that failure occurs. These kinds of distributions naturally capture that, and that is the theory that the only hope of theory underlying the Gompertz is this extreme value stuff. So this is like the gobbledygook. I don't expect anybody to even really care about this. You just know that anytime you have a distribution, that there's some gobbledygook that describes what that distribution does. And if we were in Excel, we could have just, you know, a column of ages, 1 through 100, and we could take a normal distribution with a mean and a variance and just stretch that down, and it would look, you know, kind of like this or whatever. And these distributions just happen to have this kind of slightly skewed shape because of the properties of minima and maxima. That's all. It's just that simple. But the important thing is that the Gumbel would never work to model aging because it exists at values less than 0. You can't have a negative lifespan, so what you have to do is rearrange the Gumbel so that it becomes only defined at positive values. And when you do that, you get this expression right here. And all I want you to notice is that log A is our initial mortality rate, and B is our rate of aging. And so that anytime you plot log A against B, you have B here. That's the point. And I realize that's quite boring, but the point is that they're fundamentally related just by the properties of the distribution. And this is something that only real demography dorks know, and aging people ignore it. So, why would we use the Gompertz distribution as our basis for understanding something as important as human aging? The first practical reason is that it has support for values greater than 0. And the second is that it's from this class of distribution designs to model extreme values, maxima and minima. But there's no life history model behind it. But I still think there's an intuitive sense in thinking of mortality as minimum failure times. So in a sense, I'm very much in the group of people who are very skeptical about the utility of the Gompertz. But this minimum failure time angle is your best bet for a theoretical underpinning to it. Okay? So we have a failure as that of an essential life-supporting or death-averting organ or system, and maybe death is just minimum time to a crucial failure. So within the Gompertz world, there are a whole bunch of issues that come up. Each one of these could be really several talks. One of them is the difference between intrinsic and extrinsic mortality. Does that sound familiar to anybody? So in a Gompertz world, intrinsic mortality is mortality that varies with age, and extrinsic is mortality that doesn't. Age-independent mortality. And I would say that there are very, very few sources of mortality that are important that don't interact with age in some way. And yet, almost all of our theory assumes this distinction in several different areas of ecology and evolution. It could be that the Gompertz curve only captures what we would call senescent mortality, which is something like your intrinsic susceptibility to death from environmental insults. But what is that? What is this intrinsic susceptibility, and how would we even measure it in the wild? And what ages do we consider as being subject to this intrinsic mortality stuff? When does aging start? And then there are other issues with Gompertz fits. For one, mortality curves aren't a perfect straight line with age. They tend to bend and do all this other stuff. So we have to make special modifications to it to account for theoretical deviations from the straight line. And most importantly, these parameters, log A and B, are negatively correlated, and people spend a lot of time fretting about that. Okay, so this is the Strehler-Milband correlation, the second major point. This is this correlation between these two parameters, and it is almost intuitive, but not. Okay, so this comes from a paper in 1960 where these two demographers studying aging fit a bunch of Gompertz models to a bunch of different populations, and they noticed basically that they've written it with different letters, but basically that the initial mortality rate and the rate of aging were strongly negatively correlated. Here's a plot from a later paper. I didn't put the year. This is just a few years ago. And so they've written it differently, but here's our initial mortality rate, our log A, and here's our rate of aging. And what this tells us is that when initial mortality is low, the rate of aging is fast, and it's supposed to be the other way around. So here's Resnick's guppies. Resnick is an ecologist who's done a lot of really important work on aging and all kinds of ecology, really. And his study organism is a guppy. And he did this one study where he got guppies that were the same species, but they occurred in nature in all these different pools that had different levels of predation in them. So there was natural background variation in predation. And if Williams' hypothesis is correct, then those who had high predation levels should age faster. And he did a bunch of Gompertz fits to guppies from these different ponds, and he found, again, this, which is exactly the same thing as the Strehler-Milbaum correlation, where our received wisdom from evolutionary theory says it should go this way, and in fact it's the opposite. And his statement was something like this: our results do not comply with the classical Medawar-Williams theory when senescence is evaluated in terms of survival. And most importantly, he says guppies from high predation localities have lower rates of aging and do not differ in reproductive senescence, da-da-da. And so he's one of the first people to really make a strong voice for an exception between theory and data, but people cite that paper, but they don't really pay attention to the fact that he was very skeptical of this correlation. So just remember that, again, we've got our underlying data is this age of death stuff, that if these are described by a Gompertz distribution, that those two parameters, A and B, have to be related. But we tend to fit data in this kind of a space. Okay, so now we're back to anthropology. Everybody okay? Was that terrible? You can say yes, it's all right. Nothing?
I have a question.
Yeah, great.
Sorry, I'm just confused about just two things.
Mm-hmm.
Back to the guppies.
Mm-hmm.
You mentioned that he used hybrids.
No, not hybrids. They were guppies that were the same species, and they naturally occur in pools that differ in the amount of predation they experience.
But you said so they were separate species, but the ones that he did.
Same species.
Oh, okay.
Same species, yeah.
Okay.
Sorry, yep.
I just got a bit confused.
Yep.
And then the other thing is, so from the Strehler-Milbaum correlation, you said that initial mortality rate and aging are strongly negatively correlated.
Right.
But so is that initial mortality under like what conditions?
The conditions of whatever population you fit the data to. So if you were to go and study some hunter-gatherers, then there would be some typical mortality rate that people at, say, age 30 experience, and that would be your initial mortality rate, basically. And then B would capture how fast mortality rises after that.
So the stronger, so if you're more likely to die earlier,
Mm-hmm.
you will age more.
Right. Yep.
But that does make sense.
It's supposed to go the other way around. The very next slide addresses this, and raise your hand if it's not clearer. I mean, when you say it makes sense, why does it make sense? Using what logic?
Because you kind of weed out people who are not going to survive the rest of their life.
Holy cow, that's perfect. That's exactly what they say. That's so great. So we have one of the things that I said was a kind of a talking point for the Gompertz was that it doesn't always fit the data across all the range that you might think that it should. So these are mortality curves from 75 to 100. And you can see that just by eyeball, it looks pretty good, And then down here, the data are going this way, but the curve is going that way. This is what's called deceleration in mortality, because mortality is going slower as age advances. Or sometimes it's called a plateau. If you have data for really, really old people, it almost seems like the data might bend. And so this is the same thing. Remember, moving from an unlogged to a logged picture. And here you can see the data coming down here below. And essentially, there are two ways in which the argument you just made is applied in this world. One is that when you have higher levels of mortality, you leave a more robust subset at later ages, and they are less likely to diverge from this line because, let's see, do I do that in the next slide? Yes. So the theory for why these deviations happen is what is called, they're called frailty models, or heterogeneity and susceptibility to death, or variation in individual heterogeneity, or something like this. So essentially, you can imagine that these are the real curves, and they're bending, but this is just a population level measure, and the population is in fact composed of people who differ in how susceptible they are to death. And if people differ in that susceptibility, and you don't know about it, you don't measure it, you only see this line. So in fact, you've got 2 or 3 populations who all age at the exact same rate, but let's say one smokes and drinks, one just smokes, and one's healthy. then that will make this bend, because as time passes, the population has more and more of these people and fewer of these people. Does that make sense? And so this is pure just theory now, where we have one set where these are populations that they differ in their susceptibility to death, but they age at the same rate, and then you get this kind of curve. And these ones have the same initial mortality rate, but they vary in how quickly they age, and you can get a really huge bend in that one. And so here's our buddy the Gompertz again. And the way that these models work that account for this is you just modify it with this S of x to the gamma. And I'm not going to talk anything about that. Just know that there's a huge toolkit of stuff that exists that helps you sort out how much of the bending here is due to variation in the population, right? That's what these models do. So there's models developed to account for this, yeah. And it's a huge area. Triffon, the second author on this, just published a paper with Jim Vopel in demographic research that is just full of integrals if you want to take a look. So a passing question, individual level variation in intrinsic susceptibility to death sounds like something that could be evolutionarily relevant, doesn't it? I mean, it seems like this is something that would be really important. Some individuals are more likely to die than others, that natural selection should have a lot to say about that, yes?
Can I just ask whether this applies to between species comparisons as well? If you pull out many different species, do you see the same thing?
In the...
So rather than just doing within fish and then within humans, you do across species comparison. The rates of age in the beginning, or the rates of death in the beginning, will also correlate negatively with rates of age.
Isn't one of the plots?
Yeah, one of them in a minute will show that. No, I haven't done one across species yet. That's guppies. These are all countries.
Okay.
I guess it would really depend. Like if you plot guppies and sheep and humans all in the same space, they're really all over the place. I've only done it for chimps and humans, so I would be cautious to guess. It's designed for within population variation, for sure.
Because then it would exclude the possibility that it's related to how healthy you are, or how well you do killing the people who are being treated.
Let's see. So in general, populations that grow slower live longer, and in principle, those ones have lower intrinsic mortality. But then again, it gets into this question of because people often equate how fast you age with how long your life expectancy is, and that's probably not a good idea. So that would, I'm not sure.
I think it would be interesting to see.
Mm-hmm.
If it's the same pattern, it probably wouldn't be related to this explanation.
Which explanation?
That it's, you are killing the ones who are not fit in the beginning, and therefore they are able to live for longer. Maybe what?
My hunch is that it actually works out in favor of Williams' hypothesis when you plot it across species. Let's see, I think the next... So, papers that have tried to make an evolutionary argument based on this stuff have recently come out by a well-known evolutionary anthropologist named Kristen Hawkes. And she basically wants it to be kind of what we've already alluded to, that when mortality is high, you kill off the weak and you leave a robust subset, and they in turn age more slowly. And so this is one of the plots from her paper, and these are chimps from captive and wild settings that they fit. And so in this sense, the chimps are parallel rather than down here. But that's also because of some modeling decisions about what age range they fit. When we did the same populations, we don't get that. We get chimps down here. So you can see that again the correlation is negative. I think it comes up to 0.96 or something in the paper. And the idea is that the rate of aging is fast up here where mortality is low. and our evolutionary theory of aging supposedly tells us it should be the other way. And so what she's arguing is that it's kind of like controlling for a quantity-quality trade-off. If people with more resources might live longer and have more babies, if you control for quality, then you might see that there's a trade-off such that if you have more babies, you live shorter. And essentially, she's saying that the same thing is going on here. So this is the pattern. There's a whole bunch of negative correlations in here that if we adjust for individual level quality, that we would in fact see the exact opposite of this. So the way that they say it in the paper is that this relationship between Gompertz parameters, this is the SM correlation, is consistent with a hypothesis of population heterogeneity and differential culling when the initial mortality rate, measured as log A, as I've been saying it, is low. More live to older ages, so the rate at which mortality risk increases across adulthood reflects the higher heterogeneity of the survivors. Very intuitive, it sounds good, and it recognizes a major disagreement between the Williams hypothesis and all the stuff we're getting from all these Gompertz bits. And to propose something that rectifies all that is a really interesting step. So this is a horribly boring slide, I realize, but I want to just lay out all of the rationale for this hypothesis at once. So we have this background life history expectation that reproductive effort should trade off against survival. We know that, and we know that we often don't see it, though, because differences in quality obscure the trade-off. So we know that longer-lived individuals often have more children. In humans, individuals who have more children have them at later ages. And so we try to do things to adjust for quality to reveal trade-offs. This is, if you're not used to hearing this, it's very standard kind of evolutionary ecology practice. And the argument would be, should we adjust for quality in this actuarial study of aging? Because if the quality distribution changes when mortality lowers, that could obscure what we see in terms of the relationship between mortality and the rate of aging. And remember Williams' hypothesis that lower adult mortality should lead to slower aging. These Gompertz fits give the exact opposite pattern. Lower mortality implies faster aging. And so we've got two different researchers, one studying guppies, the other studying humans, sort of being perplexed by the same basic pattern, this failure for data to follow this theory. And then heterogeneity is proposed to explain this pattern, and it's also proposed to be the reason for some differences in fertility patterns between chimps and humans, which I think are in the next slide. Yeah, great. So this is from these papers. You have several different chimpanzee populations averaged together. If you take individual populations, you get the same basic thing in terms of the argument. The idea is that the chimpanzee pattern starts fairly high and is flat-ish, and then drops quickly, and there's almost no chimpanzees still alive after age 45 or so. And then the human one rises steeply, peaks at a relatively young age, and then declines much more steeply. So it's more peaked with the peak coming at a relatively young age, and oddly enough, both species stop reproducing at almost the same age. Yet in these two data sets, is this the one with the Hadza or the UCB? This one is the, I don't remember, chimpanzees, humans. There's 74% of this cohort still alive when they finish reproducing in the human population, and in the chimps there's only 1%. And so the idea is that what's responsible for this is that there's more frail survivors in the human population due to low mortality, and in the chimpanzee population, the really high mortality young ages has weeded away all the weaklings, and you only have the tough chimpanzee moms, and they can make it through their reproductive years without these failures in terms of both survival and reproduction. And just to sort of articulate how much variance there is in individual reproductive quality, she has these three different data sets. There's all natural fertility humans, and one of them is age at last birth, and one of them is menopause, where menopause is roughly known. And so you'll see that, across these populations, 10% of the women have had their last birth by age 35 or even 30, whereas 10% are still going at age almost 45, right? And you have quite a lot of variation in when that is occurring. And a very similar but shifted to the right for menopause. And so there's a lot of variation in late age quality in terms of reproductive quality. So that is her argument, their argument. And then just more support for that, you see that this is the age when subject had a child, and those who lived to be centenarians, a lot more of them were still reproducing above the age of 40. So people who were living longer were also reproducing to later ages, implying that there was an underlying quality that was responsible for the pattern. Okay, so as they say it, the SM correlation is due to mortality selection. Individuals who are more susceptible to death die as early mortality culls away the weak, leaving a more robust subset. And interestingly, this preserves Williams' hypothesis. It's still true in this world. You just haven't controlled for the right variables. So the way I would think about it is we have our what the data say is this line, and if we adjust for unobserved variation in humans using frailty models and then replot the data after we fit those models to the same populations, that a weak test, a weak support for the hypothesis would be if the new correlation is still there but much, much shallower. And a strong test would be if the correlation, if the line goes flat, when in fact the prediction is even that it should go completely the other direction. So this is what frailty should do. I guess I should say that in the paper they say that the frailty models that I introduced that account for this curving of the mortality pattern, they say that those are the models that should capture this effect. So we tested this hypothesis at two levels. The first was purely statistically, where we fit, we tried to fit gamma Gompertz models. These are these frailty models to the same set of populations, and with the idea that accounting for heterogeneity should weaken or remove the correlation. And then secondly, we just thought there's so many problems with the Gompertz and the theory underlying it that it's not really a fair test if we do it purely on statistical grounds. So we've done a lot of just kind of literature review to look at what happens when people study populations that differ in early life mortality experience in terms of their late life performance. Yeah, Moya?
So why isn't your prediction that if you were able to fully measure heterogeneity, why wouldn't your prediction be that it would be positive?
Just because I already know it's not, and I didn't want to draw it. But that would be the prediction, yeah. But I would say that I would have taken as support anything from a weakening of the negative.
That would be support for frailty having part of the effect, but it wouldn't necessarily support Williams' models. So.
Right.
Okay.
I agree. Yeah. Does everybody understand what you're saying? Yeah. But I think that we're probably not all equally familiar with Williams' hypothesis. So I just want to note again that there's very contrasting views about the Gompertz and its underlying theory. So we have this quote from Wood et al. 1992. This is about the Strehler-Milban correlation, right? The initial mortality rate and the rate of aging, log A and B, are summary measures derived from untestable fit of an atheoretical model to imperfect data and may only approximately capture the age pattern of mortality for any particular species. And the other view is that the Strehler-Milban correlation captures a fundamental evolutionary trade-off with implications at population and species level and individual level. And I started this analysis on this side, and now I'm very definitely on this side, if that's not clear. So we did a bunch of model fitting. These are the populations that we use. They're fairly typical for evolutionary demography studies of cross-cultural variation. There are some hunter-gatherer populations that we couldn't use because we needed actual exposures, but don't worry about that. And you can just see how different the populations are in terms of life expectancy at birth. The wild chimps are down at 15 and 11, whereas France 1910 is 62 years. We have old populations, right, because we're following cohorts. So these are people who were born in 1910. You can't go more recently because those people are still alive, right? Okay, so this is what our fits look like when we plot our Strehler-Milban correlation. One thing to note is that these are our chimps, and in the Hawks et al. Paper, the chimps are up here, and for ours, they're down here, and including them or excluding them from the analysis doesn't change the value of the correlation. And I think that's because we fit a different age range, because it's one of the critiques of the Gompertz is it doesn't actually say when senescence should start, and people are quite haphazard in what age they select to start with. So Hawks et al. Fit starting at age 30, but most chimps are already dead at age 30, so we started at 15 or 20, I actually don't remember. All of these ones with big error bars are the hunter-gatherer populations. They were very hard to fit, even though it looks like the correlation might not be there if we did just the hunter-gatherers. It is, and I think this one is an error. It was really hard for that model to fit, so if we had that one out, then it would be very clear. The strength of our correlation is weaker than what other studies have reported. It's about 0.7, whereas other people get usually 0.9, 0.95. But the fact is that it's there, and then what I wanted to do when I approached Triffin about this project, the idea was that we would fit gamma Gompertz models to the same data sets and then see what happened, right? And the extremely, this is so funny. So nobody's ever done that. There's all these studies looking at the Australia-Milband correlation, and there's all these studies about frailty, and nobody's actually just said, hey, what happens if you fit frailty models, and then we plot the Australia-Milband correlation. And when we did it, we got this result, which in fact is almost no result, that the gamma, the stuff that accounts for the variation that you don't see, it was insignificant in every single one of our populations, which means that if you just assume that everybody's exactly the same, you get the same answer as if you assume that there's a lot of variation in quality. So this is like really poor support for the hypothesis, and it's obviously not the only issue I have with their work, but I really did not. I was really bummed when this happened, and we'll talk about, I think, in the next slide why that is. So basically, the gamma Gompertz model, the stuff that accounts for individual level heterogeneity, didn't explain any of the variance in the survival patterns at all. And I think why that is two major reasons. One is that you'll notice that this deviation from the Gompertz fit happens at very late ages, 95, 105. And from basically all the populations we have, there's almost nobody left at those ages. And so I think that it was a mistake to assume that frailty models measure quality in the way that they hypothesized. In order for frailty models to do much, you really need to study survival at ages 100 plus, and there's very few populations where you can do that. I don't know, do I say this? And so what I think is that there's been a recent upsurge in trying to claim that frailty models are useful for evolutionary studies in all kinds of populations. But in fact, what a demographer means when they say heterogeneity is not the stuff that natural selection acts on at all. It's a mistake to equate them. So these frailty models start with people who study like light bulbs, right? Like you have the world's best light bulb factory, and they make 1,000 light bulbs, and they turn them all on in totally controlled conditions, and the light bulbs fail at different times. And I mean, maybe there is some little material flaws in them, but supposedly they've controlled for all that, and there's not. So, and you can do the same thing where you take exact genetic clones of Hydra or Daphne or anything else, you raise them in the exact same conditions, and you get tons of variation in mortality. That's unobserved variation, but it's not intrinsic differences in quality of the sort that we care about. And I started this project kind of making that mistake, thinking we're the same, but I realized that I am not the only one, right? That there's a lot of people who are wanting to use these frailty models to ask evolutionary questions, and that's probably not a good idea. Just to take it one step further, because our gamma models were insignificant in every case, we just simulated data. Triffin simulated data. I didn't do that, of course. And you can see that if you just take populations and resample them, I think I'd have to actually look at the notes. These are populations of 100,000 that we just refit, and you get an exact, perfectly -1 correlation, which, if you remember the weird little mathy bit about moving from a Gumbel to a Gompertz, we get exactly what we would expect from that transformation when we look at actual populations that age according to gamma Gompertz mortality. Just as an aside, I just put this in as when I was in Lucio's office. This is a paper that came out in 2009 that looks at survival and reproduction between elephants and killer whales. And you see that they're actually kind of the same as the chimpanzee curve and the human curve. And then you would think, well, there would at least be some support for the Hawks et al. Argument if the population that's gray had higher mortality during reproductive ages than the population that's black, and indeed they do. So this is the best bit of anecdotal support that I have for their argument, but there's way more on the skeptical side. So from a statistical standpoint, there's almost no support for the idea that unobserved heterogeneity sensu frailty models is responsible for the Strehlen-Milban correlation. That said, mortality culling must have some effect on just composition in age at late ages, composition of the population at late ages. And it may be the case that isolating very advanced ages only would reveal the basic expectations of the hypothesis, but these are going to be ages that are really novel in terms of having very many people live to them, like ages 100 plus. And the heterogeneity accounted for by the frailty model may be totally different from the heterogeneity that natural selection acts on. Quality is not at all captured. The individual variation in quality is not captured by these models at all. But that is what they proposed. We didn't propose that. So empirical evidence, like we have all these problems with the Gompertz. We have the fact that the correlation between log A and B may well just be a statistical artifact rather than anything meaningful for biology. And that could obscure our ability to see the effects of reduced mortality selection on late life heterogeneity. And so what you can do is there's tons of demographic studies that basically capture late life performance and early life mortality or early life variation exposure to different things. So this is one. These guys in the demographic world call this scarring versus selection. So does stress leave scarred survivors or the most robust subset? And the answer, if you look across a bunch of these studies, is basically that sometimes yes and sometimes no. And your intrinsic susceptibility to death may actually be negatively impacted if you go through something that raised mortality for the population you're in. So in this case, they had POWs, and so severely stressed former Union Army prisoners, those younger than 30 in imprisonment faced higher old age mortality and morbidity and worse socioeconomic outcomes and everything. And those who were older than 30 at imprisonment faced lower older age risk of death, and they were in better shape overall. And so it seems that sometimes when you lower mortality, you totally homogenize the developmental experience, and you actually make it so that people are more robust in late life, which is exactly the opposite of the heterogeneity hypothesis. And I would say that's what's happened in countries like Sweden and the UK and the US. A more convincing one is this study in The Lancet from last year, where they had two Danish cohorts. They were born 10 years apart, 1905 and 1915. Not a big gap, really, but a lot happened industrial revolution-wise in that period of time. And so there was much greater odds of reaching age 90 plus in the 1915 cohort, the latter one. And the 1915 cohort scored better on measures of both cognitive and physical performance. So more of them lived to that age, more of them were in better shape mentally, and more of them were in better shape physically as well. So this would be the exact opposite prediction as the heterogeneity hypothesis. And then there's just, we could look at a whole bunch of graphs like this. This just shows that variation in age at death is actually smaller in those with higher levels of education, and those with higher levels of education usually have lower mortality at all ages. And so if it was the case that being educated led to more frail individuals surviving to late ages, there should in principle be more dispersion in probability of death at late ages, but there's in fact the opposite. So there's not much clear evidence for the relationship that increased early life mortality and reduced variance in performance or increased robustity at late ages. Many of the things that increase mortality also increase scarring among the survivors, and there's quite a few different processes at work here. And I would, I guess, just suggest a counter view that improved conditions homogenize early life survival, leading to less scarred and more robust survivors at late ages, the reverse heterogeneity hypothesis. So the last little bit, this is for aging nerds, really, but I mentioned several times this Williams prediction, and so the Williams prediction states that when mortality is high, aging should be fast, or aging should be early. But anytime you read a paper about some biological study of aging, they're going to cite three people: Medawar, Williams, and Hamilton. Don't worry about the difference right now between Medawar and Williams, but those two guys combined are what we call the classical theories of evolution, of aging, and all they really say is that the ability of natural selection to get rid of bad stuff diminishes with age. That's easy, right? And Williams had a verbal model, and he said that mortality was the thing that determined how hard natural selection could work to get rid of bad stuff with age. And then Hamilton came along and he recast Williams' verbal model with math, and this basic notion that mortality is the thing that determines how good natural selection is at getting rid of stuff is wrong. And he has this indicator, which is just basically how sensitive the growth rate is to a change in mortality at age, and this incorporates reproductive value and the age structure of the population, because how many other individuals there are at each age affects how valuable you are to natural selection, or how likely natural selection will get rid of a bad trait. And when you plot this indicator for these populations, you get something like this. And so this will always happen, that mutations that occur late in life are harder to get rid of than those that occur early in life. That's the basic prediction. But if you just raise mortality, you change the denominator and the numerator by the same amount, and those two things offset each other, and there's actually no prediction about what just a change in mortality does to the rate of aging. If that didn't make any sense, which it may not have, just know that when you read these papers and they're talking about Williams' prediction, because there's a lot of them that come out even currently, that you really want to read Caswell 2007, which is one page. And he says it in math and very, very eloquently in words, that in ways that anybody could understand. And so the problem is that this prediction underlies a lot of what we do when we study human life history variation. It's one of the fundamental tenets of the grandmother hypothesis. It was the fundamental tenet for the heterogeneity hypothesis I just presented. And while Resnick raised it as an issue to be resolved, it was a motivator for some really big interpretations about human evolution by the Hawks et al. Papers that I very much disagree with. So that's all. Gompertz mortality lacks a clear theoretical basis, but potential with failure times. This SM correlation should be interpreted with great caution. The heterogeneity hypothesis recognizes important tensions between theory and data, but this problem that I just showed with the Williams hypothesis removes a key aspect of its rationale. There's also very little rationale for the SM correlation itself once we realize that that's a statistical artifact. And there's not very much evidence that the Frail die first rule accounts for late life performance. And in the future, we should look at things like variation in both the onset and the rate of aging, whereas people usually ignore that you might delay when you start aging, not just change how fast you age. And then there's these things called derived theories of aging that recognize all of these problems and nobody's using them. That's all.